Hello and welcome to this video on why you should use structural equation modeling for analyzing longitudinal data. My name is Geiser. I'm an instructor and statistical consultant with QuantFish, and on this channel I present weekly statistics tutorials. On Tuesdays I usually talk about statistical analyses in the Mplus software. On Thursdays I address more general questions in multivariate statistics, including structural equation modeling, factor analysis, multi-level modeling, and latent class analysis. If this is something that interests you, then please subscribe to this channel. Also, don't forget to hit the like button and to check out the description for additional resources, including a link to my free weekly stats newsletter and links to free workshops and other courses. So in this video, I want to address the question of why it is a good idea to use structural equation modeling and or confirmatory factor analysis for analyzing longitudinal, or we could say repeated measures data. What are the advantages as opposed to using something like repeated measures analysis of variance or regression analysis or multi-level modeling, which is also often used for analyzing across time data? So one of the key advantages of structural equation modeling and factor analysis in general is that these methods allow us to include latent variables, and latent variables help us to separate individual differences that are due to true differences between people or true score variance, we could say reliable variance, from measurement error variance. That is to say the key advantage of SEM and CFA in general, regardless of whether you analyze cross-sectional data or longitudinal data. Those methods allow us to separate measurement error from true differences between people and to determine the reliabilities of our measurements. And so that is one key advantage, and that advantage is especially useful when it comes to analyzing longitudinal data, because oftentimes we are interested in changes across time. And so if you were to analyze changes over time in terms of different scores or different score variables, then measurement error is especially critical in terms of a different score variable, because when you compute a different score variable, for example, between time 2 and time 1 of your scores, then measurement error from both time points, or we could say unreliability from both time points, impacts that different score variable when you do it between observed variables. And so with structural equation modeling and factor analysis, we can look at latent change, for example, in latent growth curve models. Our slope or growth factors in latent growth curve models are change factors or latent difference factors, we could say. And so those are then corrected for measurement error, which means that we can clearly separate true changes over time from variability that is simply caused by random measurement error. And the same is true for latent change score models, which you could also analyze in the framework of longitudinal confirmatory factor analysis. So that method would allow us to separate true differences in change over time from fluctuations over time that are simply due to measurement error. And that's a huge advantage, because observed difference scores can be quite unreliable, and that can be a problem when you're interested in inter-individual differences in change over time and explaining, for example, why some people change more than others. That's a question that we frequently have, for example, in psychology, when we want to know why do some people respond better to therapy, for example, than other people. Why are some people's depression scores changing more than others as a result of therapy? What other variables might explain that? Is it due to age, for example? Is it due to gender? Is it related to the therapist or the type of therapy, and so on? And so when we want to predict differences in change over time, then we want to ideally use latent change score variables, because those are corrected for measurement error. So that's one big advantage. Another advantage that the SEM framework has, and the factor analytic framework, is that it allows us to test important assumptions that we're making implicitly or explicitly when we're analyzing longitudinal data. So implicitly, when we run an analysis of variance, for example, to compare means across time in a repeated measures analysis of variance, we assume that the scores are comparable across time, or in more technical terms, we would say we assume that there's measurement equivalence or measurement invariance across time. And so in ANOVA, in analysis of variance, we wouldn't even test that assumption, or we couldn't test that assumption. We would simply assume that the scores are comparable across time. With the SEM and CFA framework, we can test that assumption by running different models with different levels of measurement equivalence across time, and then that is a testable assumption. When you have multiple indicators at each time point, you can test whether the factor loadings and the intercepts and the error variances are time invariant. And I have a whole playlist on this channel on measurement equivalence that you can check out, where I explain this in more detail, and also where I show how this can be done in the Mplus software, both for cross-sectional data when you have multi-group analysis, or when you have longitudinal data where you look at measurement invariance across time. So that's another huge advantage of SEM in CFA, that it allows us to explicitly test whether the scores are comparable across time, so that we can meaningfully interpret change score variables that are based on the idea that the scales work in the same way, have the same psychometric properties across time. So this is one other aspect. Another aspect is that the SEM framework and the longitudinal confirmatory factor analysis framework is very flexible in terms of modeling different longitudinal processes. In some cases, we might have a process of long-term trade changes, and those could be modeled, for example, with trajectory models such as latent growth curve models. Latent growth curve models themselves are very flexible in terms of modeling different forms of growth over time, linear, non-linear, modeling piecewise growth over time when there's an event or intervention in between, for example. And so they allow us to model very different processes effectively. They're very flexible in terms of modeling different longitudinal processes. Also, latent change score models could be applied in different ways to look at changes between specific time points. And in other cases, we might have a process that is better described as short-term variability around a relatively stable trade value. So a so-called state variability process, or latent state trade process, where you want to perhaps separate trade variance from state variance, or more short-term fluctuations. This is, for example, the case when you examine mood states, so emotions, where those might be relatively stable over the course of your study in terms of the trait scores, individuals' dispositions, but there might be fluctuations on a daily basis, because we know that mood can vary across the day, across the week, and so this might be described by a state variability process. And then a process like this can be described by latent state trait models, which allow you to separate state variability, state variance from trait variance, and measurement error variance, so that you can look at those different contributions from different sources or different factors. I have also here a playlist on latent state trait models and several videos in which I explain those in more detail if you're interested. I also explain latent change score models and latent growth curve models on this channel, so you can check this out as well. So that would be another advantage, that longitudinal confirmatory factor analysis is very flexible in terms of how to model longitudinal data. There are also cross-legged panel models, for example, where you have autoregressive cross-legged effects that you can model. There are models with a random intercept factor, random intercept cross-legged panel model, and so on. So many different ways to model the data realistically and find out what is the longitudinal process that we're looking at, how is it best represented, with which latent variables, and how can we separate measurement error from the systematic sources of variability. Another advantage of the SEM framework is that we get tests of model fit. When you do, for example, multi-level analysis, which you could also run to analyze longitudinal data, and you could also use multi-level analysis, for example, to estimate growth curves or analyze latent growth curve models. But with multi-level models, you have a very limited set of fit statistics that you can look at. Whereas with SEM and CFA, there's a whole set of ways to diagnose model misfit. First of all, there's an overall chi-square test of model fit, which is very powerful to see whether a given model fits. You can also do chi-square difference testing, for example, for different levels of measurement equivalence to compare different models. You can look at relative fit of a model relative to another fit to see whether, for example, a latent state trait model is better or maybe a growth curve model would be better. So you can compare different models with fit indices. You can also look at residual diagnostics, modification indices, and so on. So you have very effective ways in structural equation modeling to diagnose model misfit and to compare different models in terms of their fit. And so that's a big advantage as well. Furthermore, with SEM and CFA, you can not only look at mean changes across time. With analysis of variance, for example, you're limited in terms of looking at mean differences across time, and there might be pretty rigorous assumptions that you might have to make. For example, the sphericity assumptions. You might have to make restrictive assumptions about your variance covariance structure, and with SEM you don't have to do that. It's a lot more flexible in terms of modeling both mean structures and covariance structures, and you can look at both mean differences over time and inter-individual differences in change across time, meaning you can also you can not only look at the mean of a different score variable, but you can also look at the variance of a different score variable. And so that would mean how much people differ in terms of how they changed over time. Some people might change more than others, and then it's interesting to know why. I already mentioned that, so we often are interested in explaining why some people respond more to an intervention, or why some people change more over the lifespan in a natural way, or why they respond more to an event or an experimental manipulation or something like that. And so then we can also regress our change score variables or slope factors in growth models on covariates and try to explain why there are differences between people in terms of how they changed over time. So it's a very flexible framework that allows us to model both mean structures and covariance structures. And so that is something that is way more flexible than, for example, analysis of variance. So I hope this video helped you understand a little bit better why structural equation modeling and factor analysis are popular methods for analyzing longitudinal data. If you're more interested, then please check out the other videos on this channel that I have on longitudinal confirmatory factor analysis and change and growth curve models or latent state trait models as well. Also check out the description for additional courses. I offer a course on longitudinal structural equation modeling in Mplus, for example. And don't forget to subscribe to this channel, hit the like button, and I'll see you next time.